Hello everyone, today I'll be presenting about the mechanism of energy transfer of pipe and duct flow. And this is regarding my assignment 2. My name is Vinod Ramaya, ID number 25206, and let's look into the introduction. So, now let's take a look at pipes and ducts, another steady flow device. We are all very familiar with both types. They carry the water we use to drink and shower, the refrigerant in our air conditioners and fridge, and the hot air during the winter. Since they can be considered steady flow devices, we know that the rate of energy in must equal the rate of energy out. If we expand this equation to cover all the types of energy associated with steady flow systems, it looks like this. We can simplify this equation depending on the purpose of the pipe or duct. If we have a pipe or duct with a diameter that is constant, then the velocities of the fluids involved are relatively small, meaning kinetic energy is negligible. Potential energy is also negligible if there is no significant elevation change of the fluid. If the pipe is well insulated, there is no heat loss or gain. If there is no heating section or a pump and such, then work interactions are negligible. In that case, the most basic pipe or duct would involve only mass flow and enthalpy. Since pipes or ducts usually only have one opening and one exit, the mass flow must be the same. So it can be represented as a single variable. Now let's go through specific cases where we have to consider the types of energy we just crossed out. If the pipe is not well insulated, we can have heat input or heat loss. If there is a heating element inside the pipe heating up the fluid, then we would have work input. If there is a large elevation change, then potential energy has to be considered. If we have ducts with variable cross-sectional areas, then kinetic energy of the fluid might have to be considered. So, depending on the type of pipe or duct, we will need to consider what type of energy is involved. To tackle some of the problems, you should keep in mind that if you have a difference in enthalpy, you can use this equation to figure it out. So, all you need are the initial and final temperatures, along with the specific heat of the fluid. If a question involves heating elements, keep in mind that voltage, current, and power can be related using this equation. Let's go through some of the examples to see how we can apply what we just learned. Let's take a look at this problem, where we have an electrical heater that used the heat up air. We need to figure out the current supplied to the heater. The initial temperature of the air is 15 degrees Celsius and it's heated to 30 degrees Celsius. The initial pressure and the final pressure stay the same at 100 kPa and the volume flow rate of the air is 0.3 cubic meters per second. The voltage of the heater is 110 volts. Let's start off with our energy balance equation. The air is traveling through a duct and it's heated, so for inputs we have work input, so that's done by the heater, and we have mass flow and enthalpy. For output, we have only mass flow and enthalpy since there is no heat loss. Since this is a duct with one inlet and outlet, the mass flow will be the same on the input side and output side. Let's isolate the equation for work input since that's what we are trying to find. Now, we can factor out the mass flow. Notice how we have a difference in enthalpy. So, we can use this equation to figure it out. We don't have mass flow and the specific heat of air. Let's figure out the mass flow first. For that, we can use this equation. Remember, the problem is we don't have the specific volume of the air. We can figure that out using the ideal gas equation, since at the given parameters, the air acts as an ideal gas. To use this equation, we need the gas constant of air, which we can find from a table. So, here is the value we are looking for. Now, let's plug our values in. Remember that we need our temperature in Kelvin to use the ideal gas equation. So, 15 degrees Celsius is 288.15 Kelvin. Let's solve for the specific volume. Now that we have the specific volume, we can go back to the mass flow equation and plug our values in. Solving gives us the mass flow. Next, we need to find the specific heat of air. We can find that from a table. Here is the value we are looking for. We now have all the pieces, so let's start plugging the values in. We get 5.47 kilojoule per second or 5470 watts. How do we use this to figure out the current of the heater? Well, power is equal to current times voltage. The work input is our power. We have the voltage and all we need to do is solve for current. Solving gives us the current that's applied to the heater. So now we're going to talk about the conclusion. An electrical heater with copper coil powered by electricity was shown as our example. By this, the first law of thermodynamics said that energy cannot be created nor destroyed. And the second law of thermodynamics stated that heat transfer occurs spontaneously only from higher to lower temperature bodies. That's all from me. Thank you.